hello everybody. So now let us continue our discussion from where we left in the last lecture. In the last lecture we were talking about the formation of a monolayer at the interface of water and air, and we also looked at the formation of such stable thermodynamic assemblies at the air water interface, which results in the formation of a monolayer. And we also realized that the addition of these surfactant molecules actually decreases the surface tension at the air water interface, which now allows us the process of solubilization of these surfactant molecules can now take place, and that is also responsible for the action of soap, including spreading, wetting, and formation of emulsions. And the formation of all these and the existence of all these events is governed by the interaction of the surfactant and the lowering of the surface tension of the air water interface. Now then we realized further that when we now increase the concentration of the surfactant molecules in aqueous solution, different kind of assemblies start getting formed, and we looked at the presence of bilayer, micelles, reverse micelles, and then vesicles. So now let us go more deeply into this discussion. So to start with, when we start with a small concentration of the surfactant molecule, now we have the formation of these monolayers where the non-polar parts, the hydrophobic parts, interact with each other, and the polar parts actually stick to each other because of the hydrogen bonding interactions between the polar parts of the molecule. So the polar parts come close to each other, and the non-polar parts, or the hydrophobic parts, or the lipophilic parts, they are sideways, so they form this monolayer. Now this monolayer can now arrange to give a bilayer where again the tails, this is the tail part and this is the head part, where the tail interacts with the tail of the next monolayer such that it increases the hydrophobic interaction between the tail portions, and the hydrophilic portions are now exposed to water because we are considering water as a medium in which we are dissolving the surfactant molecule. So this forms a bilayer, and now the stacking of these bilayers, gives rise to a lamellar phase. So you have a bilayer, you have the water molecules, here, now you have the polar parts, you have the non-polar, the polar parts and the non-polar parts in between. Now the stacking of these bilayers will give you the lamellar phase, and this is a very organized phase. So you see now that the surfactant molecules are now getting very well organized into definite discrete structures, starting from bilayers to lamellar phases. And the thickness of the monolayer, essentially as we saw, is equal to the dimension of the molecule, that is equal to 1 molecule thick. Okay, and when you have a bilayer, this layer actually twice that of the length of the molecule. So that way we can decide the thickness of the layer. We can also have the formation of micelles. Now these are new chemical, these are different kind of arrangements where as we increase the concentration of the surfactant, now they start actually assuming spherical kind of shape, where the polar heads or the hydrophilic groups are exposed to water, and the non-polar heads are actually contained inside in the core. So essentially a micelle can be represented as a tiny drop of oil in water. And then we can also now look at the formation of reverse micelles, which takes place in organic solvents. So when you dissolve the surfactant in organic solvents, now the non-polar parts, the hydrophobic parts, are solvated by the non-polar solvent molecules, and the polar part are deeply buried inside, and they actually interact with each other because of the like polar nature, and the non-polar parts actually create the outer covering, and this leads to the formation of reverse micelles. Following this, there is also the formation of vesicles, and what happens in case of vesicles is that so you have these bilayers now, and they can now coil completely to form a more spherical structure. So when they coil, we now have two distinct polar regions. There is a polar region inside inside the cavity, and then there is also polar region in the exterior, and in between we have got the non-polar region. So this is a vesicle can now be thought of as a biological cell, where you can transport nutrients and ions from the outer extracellular part to the intracellular part via these bilayers, and this is kind of mimicking that of a biological cell, although this is a very simplified version of it. So we have two distinct polar parts, and in between we have got the non-polar part, which gives rise to these vesicles. We can look a bit more carefully at the spherical micelles, and in this regard we can take examples of anionic micelle with stabilization by cations. So we can have, for example, we can have this anionic micelle, where these are the negatively charged groups, and then we have got the cations, which are shown in red because of the strong electrostatic interactions which exist between the cation and the anion. The cationic sheet is also present. So we have the hydrophobic part, and this is the hydrophilic part, and we now have got different layers here which are present. So the hydrophobic core is around 1 to 3 nanometer, and we have got the stern layer, which is 0.1 to 0.3 nanometer, and then we have got the Gauss-Chapman layer, which is 10 to 100 nanometer. So in the Gauss-Chapman layer we have got these cations and anions which are arranged. The hydrophobic part is 1 to 3 nanometer, and we have got the stern layer, which is 0.1 to 0.3 nanometer thickness. And it is to be kept in mind here that the formation of the micelle only takes place at a certain concentration. So the concentration at which micelle formation takes place is called critical micelle concentration. This is also referred to as CMC, and you can actually determine the CMC for a particular surfactant molecule because there is a change in properties when micelles form, and that particular concentration at which these micelles form, which is called the CMC, can be determined with lot of precision because there is a change, abrupt change in the density, conductivity, surface tension and osmotic pressure for a given surfactant water mixture. So there is a sudden change in these properties, and that allows us to determine the CMC very accurately. The second thing is that the CMC, the value of the critical micellar concentration, depends upon the nature of the side chain or the hydrophobic part. So the CMC is strongly affected by this side chain. If you have got branched side chain, then the CMC increases. Why? Because when you have got branching, of the side chain or the non-polar part, then it is very difficult to pack the molecules, because efficient packing will lead to the involvement of severe sterics, and therefore in order to get a packed structure where you have strong hydrophobic interactions and also the packing density is high, that means in a lesser volume you need to pack large number of surfactant molecules. To achieve this particular configuration is difficult, and that results in an increase in the critical micellar concentration, because it is difficult to create the micelle core. But if you have a long alkyl or aryl chain, then it decreases the CMC, because it now enhances the van der Waals interactions between the non-polar parts. For example, in case of SDS, sodium dodecyl sulfate, at 20 degrees centigrade, when the concentration of CMC is 8.1 mole per dm cube, that it is in case of this particular surfactant sodium dodecyl sulfate at 20 degrees centigrade, the CMC is 8.1 mole per dm cube, and it is observed at 162 monomer units on an average form the micelle. Similarly, if you take the MECH2 11 OCH2 OCH2 whole 6 OH, if you take this particular surfactant molecule, the CMC is only 0.1 mole per dn cube. That is very low. So with low concentration you are able to achieve the micelle formation, and also because these are the long aliphatic side chain, they are able to assemble or contain larger number of these monomer units. Approximately 400 monomer units are present. Also, it has been observed that the formation of the micelles is more favored in the case of non-polar surfactant molecules, because when you have the polar or the charged surfactant molecules, then there exist electrostatic repulsions, and because there are electrostatic repulsion between the side groups, it tends to destabilize the micelle formation. And so when the destabilization happens, the cation is already there to actually counter this destabilization, and therefore there is a competition between the repulsion and the attractive forces. So the process of assembly of these surfactant molecules is difficult for the ionic surfactants because of this electrostatic repulsion which is present in the stern layer. However, when you have the non-polar head groups, when you have the uncharged ionic groups, they are not charged, then this electrostatic repulsion is not there, and therefore the formation of the micelle takes place in a very favorable fashion. And now the next thing which we would like to investigate with respect to micelles is the formation of the phase diagram, which talks about the different kind of structures which are formed as you increase the concentration of the surfactant. Before that, I also wanted to tell you further that you have now seen the formation of vesicles, reverse micelles, and reverse micelles is actually a tiny drop of water in oil. Micelles you have seen bilayers, and now the stacking of bilayers give rise to the lamellar phase. And you have another possibility now, that is when you have these micelles. Now you see that these are the micelles. These micelles can now stack in a particular direction to form the cylindrical phase. So you have the formation of these higher dimension structures. For example, the micelle is a 0-dimensional structure. Now you have got the propagation of these spherical micelles, like a tube-like formation takes place. A cylindrical tube forms. This is the cylindrical phase, and then the stacking of the cylinders will give rise to the hexagonal phase. So these are the new phases of the very ordered types which are formed at much higher concentrations of the surfactant molecule, and they are forming different kind of ordered structures. And it is important to see these different phases which exist in the case of the surfactant molecules when they self assemble in a solution. So, you can also have the cylindrical phase and the stacking of the cylinders to give you the hexagonal phase. Now, I have drawn here for you the temperature versus the concentration phase diagram, and let us start with the low concentration. At low concentration, you see the amphiphiles are actually free to move around in the solution. You see that they are swimming around in the solution, they exist as free amphiphiles. The moment you now start increasing the concentration, at a particular concentration which we call the CMC, the formation of the ordered aggregate starts taking place. So, now we have now crossed from the region of free amphiphiles to the micellar solution, where now there is the existence of micelles, and depending upon the local environment, that is the concentration, as you can see that these species can exist over a range of concentration and they can also exist over a range of temperature. So, temperature and concentration are the two important parameters which govern the micelle structure. So, we can have the spherical aggregates, and then the spherical aggregates can also form the cylindrical aggregates like we saw, and they can also exist a possible cubic phase. As you can see, again the cubic phase exists at a particular temperature, but at slightly higher temperatures the cubic phase gets disrupted and gives rise to the spherical or the cylindrical phases. Lowering of the temperature can give you the cubic phase. As you further increase the concentration, there is another there is now again ordering further takes place, and these cylinders, as I told you, stack together to give you the hexagonal phase. So, you have the stacking which takes place to give you the hexagonal phase, and this is now a two-dimensional structure. From 0 dimension to 1 dimension to now 2-dimensional hexagonal phase has been formed at the range of concentration between 30 to 50%. And now, if you further increase the concentration, you will get the lamellar phase which is formed here, and eventually when you will at even high concentrations you will get the inverted phase. The inverted phase now corresponds to the reverse hexagonal phase, and eventually it will lead to the formation of the reverse micelles. It will lead to the formation of the reverse micelle. So, we see now very interestingly, we start from the spherical, we go to the then we go to the cylindrical structure, that is a elongated cylindrical structure. Then we go to the hexagonal, we go to the lamellar, we go to the reverse hexagonal, reverse micelle. And also to keep in mind that when you lower the temperature of the solution, then you will obviously get a very highly ordered phase that is called the crystalline phase. But the path of self assembly starts from spherical to cylindrical to hexagonal to lamellar to reverse phase or the inverted phase, that is reverse hexagonal, and then to the reverse micelle. So, this ordering takes place in solution and leads to the formation of different phases. And the structures which are formed by the structures, which kind of structures which are going to be formed by the surfactants, they depend upon the structures to be formed by the surfactants depends on the molecular structure of the individual amphiphiles, and the nature of the packing, the nature of the compactness is dependent upon a critical, this depends on the critical packing parameter which we define as gamma. This is according to the Israel Israel-Willi theory. Israel-Willi theory, and it defines the critical packing parameter to be equal to V by AL, where V is the volume of the hydrophobic chain of the surfactant. A is the cross sectional area of the hydrophilic group and L is the length of the hydrocarbon chain. So, this theory tells us that the efficiency or the critical packing parameter depends upon the ratio of the volume of the hydrophobic chain to that of the product of the area and the length of the hydrocarbon chain. And this is what gives it the desired packing efficiency. And so, to start with, if we have got a small hydrocarbon chain, it is referred to as a cone like amphiphile, and as we increase the length of the hydrocarbon chain, it gets less, the cone like character reduces, it becomes a little bit cylindrical and becomes eventually cylindrical, and then again when we form the inverted or the reverse micelle, then there is an inversion in the shape as well. So, let us look at this arrangement. So, we have a polar head group and we have a small non-polar part. So, this is the cone amphiphile. Okay, this is the cone shaped amphiphile, which is characterized by a small value of V by L. Why? Because the volume of the non-polar part, essentially the volume of the cone is small compared to the product of A and L. Then slightly it gets some cylindrical character, and this happens in the case of the hexagonal phase, and in the case of the lamellar phase it is more like a cylindrical. It is more of the lamellar phase, and then we can have the reverse hexagonal. Okay. So, this is in order of increasing V by L ratio. So, the increasing V by L ratio, the cylindrical shape is actually for the lamellar phase. So, we have the cone shaped amphiphile, then we have the hexagonal phase, we have the lamellar phase, and then we have the reverse hexagonal. And as you can see now that if the shape is cone shaped, you have a smaller size hydrocarbon, you are able to pack the amphiphile better. So, you get much higher packing density of the amphiphile when you have got a small hydrocarbon chain. As the size of the hydrocarbon chain increases, it becomes more difficult to pack it into a more efficient arrangement, and that depends upon the ratio of V by AL. Now, keeping this thing in mind, what is the applications of the formation of these kind of so what is the necessity? We have got these vesicles, we have got the bilayers, and these are important components of surfactant chemistry. So, we have realized that these are important, and so what is a bilayer? It is an extended sheet like structure, and lamellar is, as we saw, it is the stacking of the bilayers. Now, what is important is that now how can we look at this process of formation of these bilayers and vesicles. So, to start with, what we can do is we take a dry lipid film. Okay, so we have this substrate and we have the dry lipid film. How do you form the dry lipid film? You have a solution of the powdered lipid, and by evaporation process you get the dry lipid film, and then you soak it in water. When you will soak it in water, then it will form, it will swell up, the layers will, swelling happens. Swelling takes place to give rise to this formation of this layers of the films. Now the next thing is that what can we do from these layers? Can we make them into vesicles, or can we make them into higher order structures, and so on and so forth? So that can be done. So using different procedures where we have to impart agitation to these layers. So what, when you do the agitation, for example, when you now do agitation, then these layers will start actually coming out. These layers will start coming out, and the layers fragment and curl upon themselves. So the layers can actually curl upon themselves, and this can give rise to the multi-lamellar vesicles. These are called MLVs. These are the multi-lamellar vesicles, and these are around 300 to 5000 nanometer thickness. And now we can also, when we have got these multi-lamellar vesicles, now we can do extrusion, that is mechanical extrusion, where in the process of mechanical extrusion, what do we do? The liquid suspension is forced through a polycarbonate film of defined pore size, and this will give rise to the LUVs, that is the large unilamellar vesicles, LUVs. So these essentially look as follows, and then these will give you rise to the LUVs, a much larger one. So these actually now combine to give you the LUVs. Whereas when you do a sonication, which is supposed to homogenize, the solution, it will lead to the formation of small unilamellar vesicles, which will be like these. These are the small unilamellar vesicles, and these are called SUVs. So you have the LUVs, you have the SUVs, and you have the MLUs. The size for these LUVs is 100 to 300 nanometer, and for the SUVs it is 20 to 100 nanometer. So this tells you that we are able to now create different kind of vesicles. We can have, depending upon the agitation you provide to the medium, as the layers start peeling off, and then the layers can actually curl around themselves, and when they curl upon themselves, they will form these multi-lamellar vesicles. Then the multi-lamellar vesicles, depending upon mechanical extrusion or sonication, will give you the large unilamellar vesicles or the small unilamellar vesicles. So, all these vesicles which are being formed have got interesting applications. For example, the ionophores mechanism which we have discussed happen via these vesicles in biological cells. So, with this we come to a conclusion of this particular lecture, where we have looked at the surfactant properties and the surfactant self assembly, and some of the relevance of this formation of vesicles, the phase diagram, the factors which affect the formation of these different ordered structures in surfactant molecules, and so on and so forth. And now in the next lecture we will take up more case studies related to surfactant species as well. Thank you.